Greetings, mathophiles. Welcome to a video on an integration technique called substitution. It arises out of the chain rule, although it also can be used in situations where the chain rule isn't obviously in evidence, as we'll see in one of our examples. We're going to start with an example and sort of let it lead us into the question of how the chain rule works under integration. So let's imagine that we want to integrate 2x cosine of x squared dx. And clearly there's at least potential for the chain rule to be involved here because we have a composition. We have the x squared inserted into the cosine. And so we might start out by saying, well, there's a likelihood that the sine is going to be involved, right? Because the derivative of the sine is the cosine. We have the cosine sitting here in the integrand. So we might say to ourselves, all right, what if this has in some way to do with the sine of x squared? What would that get us? Well, if we differentiate that, we get the cosine of x squared, so far so good, times 2x from the chain rule. Hey, that's our integrand. So the indefinite integral of 2x cosine of x squared dx is the sine of x squared plus a constant. Okay. Now there's an element of luck here, right? It happens to be the case that the function inserted into the cosine in our integrand, namely the x squared, has sitting out in front as a factor its derivative. So this exactly fits the format of the chain rule. But as we'll see, we can generalize the method that we're going to discuss to situations where the chain rule is not just plainly, obviously in evidence. So here's the idea behind this. If we differentiate f of g of x, chain rule says we get f prime of g of x times g prime of x. These are functions. If two functions are equal, their antiderivatives differ by a constant. So I should be able to say that the integral of big F prime of g of x, g prime of x dx is big F prime of g of x plus a constant. I could put the constant on either side. It seems more convenient over here. Now suppose big F is the antiderivative of some function little f. Then I could rewrite this line that's next to the bottom as integral f of g of x, g prime of x dx, and this would still then be big F of g of x plus a constant. And the thing about this that is maybe a little bit cool is if this was what you were initially confronted with, an integrand of the form f of g times g prime, all you have to do to get to a result after you've recognized that relationship is to anti-differentiate the f, take its antiderivative, plug the g in, and declare victory. This is called integration by substitution. And the reason we call it integration by substitution is that what typically is done is you do some renaming. So the g is renamed with some new variable. Often it's u. This is sometimes called u-substitution. Then this would be du dx. And this, of course, would still be u. And so the idea would be you can re-express your integral and then you can focus on anti-differentiating the little f. So here's a second look at example 1 with the idea that we're going to use this substitution notion explicitly rather than to just sort of wrangle the chain rule in our heads. So the integral again was 2x cosine x squared dx. And the function that is the inner function in the composition is the x squared. That's what you're looking for when you go looking for a u to make a substitution. So if that's my u, du dx is 2x, du is 2x dx. And then this becomes integral. 2x dx is just du. Cosine of x squared is just cosine of u. This is cosine of u du. That's, of course, sine u plus a constant. And then this is an appropriate moment to recall that u is, after all, x squared. So this is sine of x squared plus a constant. A nice thing about this method is that it spares you the annoyance, if you will, of having to sort of think about the g and the g prime. It re-expresses your integrals so that those are just all embedded in the u and the du, and you can focus on the thing that you sort of actually have to do, which is to anti-differentiate the outer function, the function we were calling f. Let's do another one. This will be the integral of x squared square root of x cubed plus 1 dx. And we've got the x cubed plus 1 plugged into the square root, so that might make a decent candidate for u. But then the derivative of our u would be 3x squared, and we don't have a 3. Not to worry. We can insert a constant factor of 3. We just have to also insert a constant factor of 1/3 to make it up. And of course, constant factors can be pulled in and out of integral signs. So the 3 that I need, I'll put on the inside. The 1/3 that pays for it, I'll put on the outside. And then u will be x cubed plus 1. Du will be 3x squared dx. And this integral will be 1/3 integral root u du. Pretty sweet. This is 1/3 times, let's see, anti-differentiate u to the 1/2, I get 2/3 u to the 3/2. And of course, we have a constant of integration. I'll multiply out that fraction, that's 2/9. And this is the moment where we recall that u is x cubed plus 1. And there we have it. No fuss, no muss. We've evaluated an integral that, before you encountered this process, you might consider to be rather daunting. Our final example is not going to feel particularly chain rule-y, but it is a good instance of a situation in which substitution can nonetheless allow you to re-express an integral algebraically in a way that makes it a lot more tractable. So this is the integral, indefinite integral t over quantity t minus 1 dt. And I suppose there's a composition there implicitly, right, with the t minus 1 plugged into the reciprocal function, if you want to think of it in those terms. And so what we're going to do is see what it gets us to let u be t minus 1. So du dt is going to be 1, so du is going to be equal to dt. If I then re-express this integral, the t minus 1 on the bottom is, of course, u. The dt is du. What about the top? Well, if u equals t minus 1, then t equals u plus 1. And it may or may not be immediately apparent what we've gained, but what we have gained is the ability to pull this expression into two different terms, right? We can sort of undo the addition in a way that we could not have up above. So I can write this as integral 1 plus 1 over u du. And that is awfully doable. This is u plus ln absolute u plus a constant, but u was, of course, t minus 1. And again, without breaking too much of a sweat, we've managed to evaluate an integral that might have been a little bit daunting before you became aware of this technique. So use it for good. Happy mathing.